is contained in it, since SL2R can be embedded in into SLNR, and in fact it requires a special embedding. SL2R can be embedded in many inequivalent ways into SLNR, and there is the so-called principal embedding, which I will maybe sort of constructively show you. So there's a specific embedding of SL2R inside the SLNR, which is how gravity sits inside this higher spin theory. So let me just very quickly mention it and then stop. So basically, you take these JAs, which are the SL2R, or I mean, I wrote down for you the J's and the L's. So now let me just go back to the J's. So you take J to be in the n-dimensional representation of SL. So the n-dimensional representation of SL2R. So just like SL2R is SO2, 1, for many purposes, SO2, 1 is very similar to SO3, which is, you're familiar as the rotation matrices. So these J's are essentially like the rotation matrices, except there's some additional I's because of the SO2, 1. So for the rotation matrices or the angular momentum matrices, you are familiar with the idea that you have representations of all integers, right? I mean, you have angular momentum, the 2 by 2 representation corresponds to the spin half, and the 3 by 3 to the spin 1, and the 4 by 4 to the spin 3 half, and so on. So those are all the angular momentum representations. So for any integer n, you have n by n representation of the SO3. You write down in your quantum mechanics class, say for the spin 1, you write down some Jx, Jy, Jz, which are as 3 by 3 matrices, and you could go on to write 4 by 4 and so on. So you take these, so the way in which you do this embedding is to consider the n-dimensional representation of SL2R, which is these are 3 n by n traceless matrices, because they are SL2R generators. So I claim that if you now start with this J and construct TAB, which is equal to if I construct, I take these are n by n matrices, so I can take the product of them, symmetrize over A and B, and remove the trace. So removing the trace means just minus 1/3, minus 2/3 eta AB, J squared. J squared is J A. So if I just consider this combination, so I claim this, so these are also n-dimensional matrices because they are products of them, and because I have removed the trace, these are also traceless. But now these transform in the symmetric traceless representation of SL2R, and then I can so on construct the A1 to AN and again I construct the symmetric traceless combination of these J's, n of them. So I go on and do this up to my maximal n, and I claim these are n square minus 1 independent traceless matrices with s equal to 2 plus 3 plus so I'll justify this a little bit more tomorrow. So and these generate the whole of SLNR, because SLNR has dimension n square minus 1. So the Lie algebra of SLNR is generated by all these independent matrices. And we'll see that these will correspond to the higher spin fields of spin 2, 3, all the way up to n. But talk about that tomorrow. Okay, so thank you.
Questions or comments?
So for n, you get a consistent theory of
so that's a good thing. I think I mentioned in my first lecture that Fradkin and Vassiliev showed that you needed an infinite tower of higher spin fields if you had spin 2, spin 3. So that's generically the case in any dimension, but in 3 dimensions there is the special possibility, which Vassiliev had not initially noticed, but some others pointed out afterwards, that you can have a consistent truncation up to any maximal spin that you want, but you have some all the spins, let's say from 2 to n. So this is a possibility that is true for 3 dimensions, and it's essentially because these higher spin fields are sort of topological or don't have dynamical degrees of freedom because they are given by Einstein-like theory. So you have the possibility to describe them just a finite number of them in 3 dimensions.
How to understand truncation in Moya product?
So I will say a little bit maybe in the next class about the most general algebra that is there, and one can show that in that algebra there is sort of an ideal that appears when there's a parameter in the algebra when you set it equal to n, the Moyal product or this Vassiliev star product reduces to ordinary matrix product. But it's a non-commutative product, and that's what this A wedge A is, a sort of a matrix product that you have over.
High spin, we believe that high spin theory is a U-free limit of a string theory. How to prove this thing here in 3 dimensions?
So in 3 dimensions, you can embed some of these theories, not these SLNR theories, but the more general Vassiliev theories. In the more general Vassiliev theories, there is a special class of them which you can see as a limit or as a subsector of, let's say, string theory on ADS 3 times S3 times D4. which is one of the string theories. So indeed you find that amongst the massless sector of that theory, at a special point in the parameter space, there is a higher spin algebra.
How to see truncation from string point of view?
So the truncation is the statement that these so the way you conclude about this is not directly from the string theory, but from the conjectured holographic dual for this ADS3 string theory. Namely, there is a two-dimensional CFT called the symmetric product CFT, and in that CFT you see that the operators corresponding to these gauge fields, they close amongst themselves under the OPE. They are a very simple subset of the operators.
More questions?
So from the transformance theory point of view, A and A tilde are independent gauge fields. But here, the transformation is A is according to B and A tilde is according to B inverse. Is there a reason for that?
So A and A tilde, so this actually, I mean, at some point I moved to the Euclidean formulation. In the Euclidean formulation, A and A tilde are part of SL2C. And then they are kind of conjugated in SL2C.
Yeah, but your B is still real.
So here B is real because I've chosen it in this particular form. But in the so this in general, I mean, there is I don't know about the deeper significance of it, but this is just a convenient way in which you can write down all the solutions of the flat connections with this boundary. But some deeper significance of that, I'm not sure if that's what you are asking.
No, because from the gravity point of view, the allowed transformation is the local Lorentz, which is just one copy of SO21. So I don't understand why in transformance point of view there are two different.
No, actually there are, so there is the, I didn't go into that in detail, but when you go to the frame formulation, you actually double the gauge transformations, because there is the local Lorentz transformations and the diffeomorphisms, both. So it is both together that give you the two copies of SL2R. So it's not just, so I didn't go into that point, but this is true in the frame formulation, that you sort of increase the number of gauge, increase the redundancy. So now there is both the original diffeomorphisms as well as the local Lorentz.
So for high spin, do you allow the actual SLN gauge transformation, or you only allow?
SLN gauge transformation. That is indeed the part of the, so the SL2R gauge symmetries are a small part of the bigger gauge transformation. So yesterday I was talking a little bit about the higher spin theories, and for each spin you have a gauge transformation. So in addition to the original diffeomorphism. So all those gauge transformations together are combining into this bigger SLNR transformation, but they are intertwined. I mean, the diffeomorphism cannot be separated out from the others. They are all part of a bigger nonlinear gauge transformation. So you can see that feature very nicely in this SLNR, which is more difficult to see in the full Vasiliev theories in general. But here this is a simple toy model of that full nonlinear structure.
If no more questions, we thank the lecturer again. We should meet on schedule, so that 2 o'clock in the afternoon.